Hello there, Mr. Sutton here, bringing you this lesson on arc length. In this one, we will be finding the length of a curve over an interval, and for the real-life application, we'll be determining how long a wall needs to be. For the warm-up in this one, pause the video and see if you can find the length of this curve from 0, 0 to 3, 9. Alright, now there's no way we actually know if to find this length. The best we can do on our first attempt is to just try to approximate it, maybe by drawing a line from 0, 0 to 3, 9. And, we could do the Pythagorean theorem on this line. So square root the change in x squared plus the change in y squared. So let's see, that would be a delta x of 3 and a delta y of 9. And then if we use the calculator, like so, we end up with about 9.487, which is fine as far as it goes, but we know it's not the true answer. So how could we do better? Well, as a second attempt, we might try drawing more line segments. Maybe make 3, like a segment from here to here, another segment from here to here, and another segment from here to here. And if you found those each individually and added them together, well, then you've got a more accurate answer. But still not quite accurate, right? So how could we do even better? Well, kind of going along this path, what if we used an infinite number of tiny line segments? So what would these look like exactly? Well, each of these would have a special length. We couldn't use just a regular delta x anymore if these things are infinitely small. We'd have to use the square root of dx squared, right? An infinitely small change in x. Plus, we can't just use a regular delta y. We have to use dy squared. So this is the inspiration for the arc length formula. For a smooth curve, that's a function where its derivative and the function itself are both continuous. The curve length for y equals f of x is given by the following formula over the interval from a to b. So we're going to have an integral from a to b because we're adding a bunch of things together, and we're basically putting this stuff here inside the integrand. I'm going to be a little tricksy though. I'm going to factor a dx squared out of everything in here. That would leave me with the square root of 1 plus dy over dx squared. And that dx squared that I just factored out, I'm going to square root it and bring it outside here as the dx in the integral. So basically, this is just using Pythagorean theorem and adding up an infinite number of tiny little segments. Now that we have a formula that lets us find the distance of any curve, let's take it for a spin. Let's say that Archie wants to build a wall around the borders of Archie Land shown here in the diagram. We want to know how long in miles the curved part of this wall needs to be. So pause the video and see if you can use that formula to figure this out. So you probably noticed with that formula that you need limits of integration. And if we're integrating with respect to x, that means we need this spot right here. This other spot we know, this is 8, but this first one we got to find. To do that, we can set f of x equal to 0, namely the x-axis, and solve that on the calculator. So on the calculator, I've entered f of x as y1, and let me set my window to be between, let's say, 0 and 8. So window 0 to 8. Let me do zoom fit, zoom 0. And hopefully we can see that x-intercept on there. So it looks like it's going through the x value 1. But let's do a second trace, zeros, option 2 there, just to be on the safe side. So let me move a little bit to the left of that and press enter. So we got a little bit to the left, a little bit to the right, enter one more time, and it's not exactly 1. It's about 0.9515. So I'm going to quit out of here, and I'm actually going to save that value as alpha A. It doesn't really matter which letter you choose. And then on paper, let me note that I've done that. So let's let that be A, that value right there. So now we can take an integral from A to 8. We still need to figure out what we're integrating, though. We're going to need the derivative, dy over dx. So let me figure out what that is. So that's going to be, let's see, derivative of e to the negative 2x. That's negative 2e to the negative 2x. And then 3 ln of x, that's going to be 3 over x. So let me plug this in my calculator now. So now I've got this plugged in as y2, and I can use it whenever I want. So now that I have that, I'm going to have the integral for my length, the integral from a to 8, and I'm going to need the square root of 1 plus this dy over dx that I just found squared, all with a dx here. Let me do that on the calculator. So here's what I've entered on my calculator. I did math 9 to get integral. Alpha A, 8. I've got the square root of 1 plus y2 squared, because again, that's where I stored my dy over dx. And let me press enter. That comes out to about 9.760, and that's going to be in miles. On this next problem, we're given the function x equals the integral from 0 to y of tan of t dt on this interval, and they want us to set up but not evaluate an integral to find the length of the curve. So this is a little bit of a game changer because this is a function defined in terms of y rather than x. The good news is, for an x equals f of y function, there's a pretty similar integration arc length formula to what we used earlier. Instead of having the square root of 1 plus dy over dx, we're going to have integral from a to b square root of 1 plus dx over dy squared. And then we'll have a dy. Basically what happened here is we factored out a dy squared and square rooted it instead of factoring out a dx squared. Same idea though. So using this formula, see if you can set up an integral to find this length. All right, so we are going to need limits of integration again. We've got them, 0 to pi over 6. We're also going to need a dx over dy. So for that, we just have to take the derivative of this function, which it looks nasty at first, but it's actually nice that they gave us this integral because our derivative is just going to be tan of y, just using our fundamental theorem. So that'll be our dx over dy. Plugging that in, we have integral from 0 to pi over 6 of square root of 1 plus tan squared of y, dy. And you could leave it like this, but if this were a multiple choice question, this would probably be simplified. So if we wanted to take this a step further, we know that 1 plus tan squared is equivalent to secant squared, which we could then square root to get just plain old secant of y. So on multiple choice, this is most likely what you would see. We're going to do one more problem. This time they want us to set up an integral and evaluate it without a calculator for this one, so a little bit of everything today. This time we have a parametric function to deal with. So as it turns out, yes, there is an arc length formula for parametric functions. In this setup for parametric length, we're still doing integral from a to b, square root, but this time the things that are being squared inside are going to be dx over dt and dy over dt. Those are both being squared. And the differential is a dt. Yep, what happened here is we had a dt squared that we factored out of everything and then square rooted. Still the same idea. So pause the video and finish this one off with this formula. All right, so we need the derivatives in terms of t now for each of these. dx over dt, and by the way, our integral is going to be from 0 to 2 pi here. So dx over dt, that's going to be negative sine of t, so we'll be squaring that. And dy over dt, that's going to be cosine of t that we're squaring. And they said we can't use a calculator, so we have to simplify this a little bit to a point where we can actually apply the fundamental theorem. So this is going to be the square root of sine squared plus cosine squared. Now this might tickle your memory a little bit because we know this is equivalent to 1 inside that square root. So that means the square root of 1 is 1, and we're just taking the integral from 0 to 2 pi of 1. This is essentially just a rectangle with a base of 2 pi and a height of 1. Well, that's just going to be an area of 2 pi. So that is it for arc length. Till next time, Mr. Sutton signing off.